It's going to be intense. Please try to understand as much as we can. And I already asked the guys a bit to keep it more conceptual, to keep it about trying to explain to you the principles. There is a huge mathematical background there, a book which is that huge, but of course we don't have time to go through that. The important thing is to understand the concepts behind the ideas, and that is also something that will help you during the lab, because the lab, it will give you more details on this thing, so we'll go deeper and deeper. But here is just to understand the main thing, so when you start doing the lab every Thursday, you are able to follow what we're doing step by step. Okay? Mm-hmm. So, enjoy it. Okay.
Thank you very much. As Simon said, this will be linked to the next lab we will have every Thursday, okay? I will try to point more or less which will be the topics of each of the lab. But I mean, here will be like an overview, and then we will go more deeper in different aspects of digital communication. So let's move on. This is divided in 3 parts, okay? So first part will be just introduction to digital communications, so some basics. And we have a digital transmitter, digital receiver, and then some basics about modulation, detection, call shaping, limited functions. This is the first part that I will cover. Then my colleagues will cover the other parts about synchronization, transmitter impairments, frequency time phase, and then Stefan, the third part, will cover the channel and channel equalization. Okay? So in this first part, so just to link with what you have seen already in our lessons. So we, as far as I know, we talk about link budget, about payloads, about transmitting power, receiving, and so on. Mainly this occurs in the analog domain. Okay, so let's say you have been working in this part. What is an LNB, the feeder, the antennas, and so on. You have more or less a view of this. But in this lecture, we will talk more about the digital part. So, let's say in a receiver and a transmitter, we can well distinguish between the analog, which is the amplifier, the antenna, and so on, and what is the digital part, okay, where you actually do many things to transmit and receive correctly the information. And this, I mean, this applies for satellite communications, but actually for any communication system. So, what is a digital communication system? What is the main purpose? The main purpose is, of course, to communicate, to transmit some information from a source, an information source, to an information destination. And this, we want to do it via a channel. Okay? So a channel is a medium where this information goes through. Okay? In satellite communications, it's very clear. I mean, this channel is the air. So you have the satellite over the sky, and then you have the receiver on ground, and then the channel, the medium where the information is transmitted, is the air. Okay? But actually, in any digital communication, you can have like wired, or you can have optical fibers, you can have another channel, or another medium. And let's say what transforms or adapts this the information to the channel is called transmitter, and then what recovers the information from the channel to the information destination is called the receiver. And these two guys are the ones that let's say act as a bridge, so transform the information that can be, as we will see later, analog or digital, to this medium, in this case the air. And then the receiver does the opposite. So, which kind of information sources or destinations? They can be analog and digital, but in the analog, I mean, some examples are like voice or sound that are natural forms of analog information. But you can have digital sources, like it's like text or data or any information generated from a computer is going to be digital information. And there is we have some methods as well to transform analog information to digital information, to then digitally process it and transmit or receive via the channel. So, as I said, this is the main diagram of these main 5 blocks in the communication system. But now let's see what is inside this transmitter and receiver. So actually, don't be scared about the number of blocks we have here. I mean, you don't need to know all of them, because actually, so in all these blocks there are only few that are in every single digital communication system, that are the ones that are in dark gray. Okay, so modulation, pulse shaping. These are like required blocks, and the other like are optional. You may find in some applications, you may not find in other applications. And whatever we have in the transmitter, in the upper side, we have the reciprocal in the receiver. Okay, so when we have compression, then we have decompression on the other side. So this has to be balanced. Whatever you do in the transmitting side, you have another block that undoes the transformation of whatever thing you do. So let's quickly go through these blocks. So this is called format. Okay, so format is a way to say transform from analog to digital. Okay, and this you will have when you have analog information source. And of course, on format is digital to analog. Another thing I want to say is that this analog to digital conversion, you may have it in, let's say, twice. Okay, if you have an analog information source, then you convert to digital. Then you do all this digital processing we will talk about. But then before transmitting, so before you go to the antenna, okay, you have to convert again from digital to analog. Okay, so maybe this formatting operation you have it twice. Once here, and then here digital to analog. Here the opposite, analog to digital, digital processing, and then if applies, if the destination is also analog, if speaker for instance, then you do digital to analog again. Okay. So another block is compression. Compression is like you remove some redundant parts of your information. Okay, and then you put it in another format so you can recover. Usually, this when you zip a file, this is what happens. You remove some part of the information, but you can still retrieve that. This is if it is lossless compression. If this lossy is like when you send a picture via WhatsApp, this is like lossy compression, but you can still see the picture. I mean, you will lose some quality, but you can see the information. Encrypting, so it's like you encode a message in such a way that only, let's say, the transmitter and the receiver can understand that, but not the others. Encrypt and decrypt. Then we have encoding. So encoding is like you add some redundant information, something additionally that gives you some information in order to correct some errors in the transmitting channel. This is called encoding. Then multiplexing is very easy. It's like you have different sources of information, and then you mix all together in the same communication channel to, let's say, to reuse the transmitter, for instance, and then you undo this process in the receiver as well. Then we have modulation. As I said, this is one of the most important blocks. Modulation is a mapping between bits. Okay, we have digital information in bits, and then we map into a complex symbol. So this complex symbol is usually called the signal itself, or the waveform. And this complex symbol is the one you can transform to the analog domain to then transmit over the channel. Then, when you do this modulation process, what happens is that maybe you are using more than the bandwidth you are allocated, okay? And then to solve this, we use this operation that is called pulse shaping, that basically changes the shape of this signal, this waveform, to fit into a determined bandwidth. Okay, so these two we will see in more detail afterwards. Then another optional block is the spread spectrum. So spread spectrum are some operations, okay, that basically you then spread your signal in the spectrum, okay, although you're, let's say, overlapping with other channels, but this is an operation that can be undone, okay. So basically, this is used for secure communications, or avoid that someone is listening at you, because basically the power is spread over the spectrum. Okay, but it is something that can be undone in the end. Basically, it's for protection of the signal, let's say. Then we have multiple access, which means that you are using the same channel for in the different time. For instance, you have in a base station for a mobile communications, you have time division, multiple access, which means that now the base station is sending something to one mobile phone, and then the other, and then the other, and this is repeated. So this means multiple access. When this is done in time, it's called time division multiple access. And this can be done also in frequency, in space, and code, and many other domains of the channel. Then we have the transceivers, that are the ones that get the information from the digital domain and then puts the signal in the bandwidth just to get into the antenna and then be transmitted or received to the satellite or from the satellite. And then there is one very special block that is only the receiver, let's say, that is called synchronization. So imagine that basically, I mean, this is someone talking and someone that is listening, okay? But they have to talk and listen at the same time, let's say. When one talks, the other has to receive at the same time, okay? So, but also this is time synchronization, but also you can have synchronization in frequency. So maybe the receiver is not looking at the right bandwidth, so they have to synchronize to the same bandwidth that the transmitting is receiving. So this is a, let's say, exclusive block of the receiver that basically you match everything, time, frequency, and phase, to be able to communicate between transmitter and receiver. And then we have the channel, basically, as I said, is the medium through which the, let's say, the information goes from the transmitter to the receiver. This is more or less the explanation of each one of the blocks. So as I said, now I will talk more about these essential blocks, modulation and pulsating, also formatting a little bit. And then in the other part, Juan and Stefano will talk about synchronization and the channel impairments and polarization. Okay, before starting in talking about the other blocks, let's have very clearly which are the figure used for. Yeah.
So before you move on, I'm not sure what the difference between modulation and pulse shaping.
Okay. I mean, these two, which are the essential ones, and maybe they are more complicated, we will talk in the next slide about these two. It's just modulation and pulse shaping. Okay? So the others are fine. Yeah. Okay. So, which are the performance metrics we use to assess how transmitting and receiver are working? So the first one is SNR. I think you already heard about in the other lectures. But basically, it's the power of the usual signal divided by the power of the noise. Then bit error rate, which is the number of bit errors divided by the number of transfer bits. This is a second, let's say, measure of the performance of the system. And then a third one is just the throughput, which is, let's say, the final goal is to increase the number of transfer bits per time. And then if we want to do a good design of a communication system, we will try to optimize all these parameters. That basically is with the reduced transmitted power, we want to increase the received signal to noise ratio, decreasing the bit error rate. At the same time, we want to utilize the system as much as possible, so it's all time transmitting, all time receiving. Use as less bandwidth as possible, because actually it is a limited resource. Actually, you pay for that, for the utilization of the spectrum. And the ultimate goal is to optimize, let's say, to increase the throughput of the system. So let's move on into, let's say, one of these very important blocks that I was saying is the formatting. So formatting is go from analog to digital domain or from digital to analog. Okay. Actually, usually, I mean, this is done with one single chip. When we're talking about hardware, that is the analog to digital converter or digital to analog converter. And what they do is there are 3 steps. Okay, sampling, quantization, and pulse coding. Okay, so the first one, the sampling, is one of the, let's say, most important ones in the signal processing. That is, imagine we have a signal from a microphone, okay? This is the amplitude. Then we have a continuous signal, okay? It's something, a voltage that is varying in continuous domain. And then sampling means that we take some samples at equidistant time, okay? This time is called the sampling time. And then, let's say, we only take the values at these specific moments, okay? Let's say the inverse of the sampling time is called the sampling frequency. And then this is how we transform continuous time to discrete time, okay? So we get these points. Next step is quantization, okay? Sorry, first I want to mention something that is very important. This is the Nyquist-Shannon sampling theorem. So this is very, very important in digital communication and in signal processing. There is a sufficient condition for a sample rate that permits from a discrete sequence already sampled to recover the analog information. Okay. The most important thing of this theorem is the Nyquist criterion. Okay, that says that the sampling frequency should be larger than twice the bandwidth of the signal. Okay. So this is the condition that has to be fulfilled to undo the sampling process. Let's say. You want to go from discrete time to continuous time. This has to be fulfilled. Bandwidth, I have here like a definition that can say that this is just the difference between the upper and lower parts of the occupation of the spectrum of the signal. And then when we're talking about spectrum,
can we go back to the next? A previous one. Yeah. So when we are saying the bandwidth of the signal, are we talking that from one crest we should take at least one sample? Is it something like that? What exactly is the Nyquist criterion?
Okay. So this you cannot derive directly from the time shape of the signal. Let's say you have to look into the spectrum. Okay. So how you get the spectrum? This was what I was going to explain. This is the Fourier transform. It's a way to estimate the spectrum of the signal. Okay. But let's say if you look at the signal in time, of course, depending on the shape. But let's say in general, you cannot say this is the minimum sampling frequency. Okay. You cannot assure that. You have to check that in the spectrum. So how do you calculate the spectrum? Using a tool that is very useful in signal processing, very used. That is the Fourier transform. That is a transform. Okay, we are not going to enter into the maths, but you have to understand that this is a tool that you apply into the time signal to go to another domain that is the spectrum domain. Okay, so basically it's telling you this signal has this spectrum, and then when you check the spectrum, you can the bandwidth of the signal is the space in the frequency domain that this signal is occupying. Okay, more or less.
I can describe more because
Okay.
I was facing it in my thesis. I was analyzing my output data from an energy harvester, and in my data there were some noises. And professor said me that use fast Fourier transform and convert them and get the noises, cancel them, and use the inverse IFFT to have the exact data, and the Fourier function converts my data was voltage per time that I used to have frequency per time.
No. not frequency per time, but let's say voltage or power, and then here you have frequency.
We have DSX.
Yeah.
And
So, and you say this fast Fourier transform is a digital implementation and fast implementation of the Fourier transform, which is, let's say, the original of the concept. So, more or less what you have. Okay? Imagine that we're looking at the black signal, right? This black figure. Imagine this is time, okay? So basically you have 0, and then something that is 1, and then something that is 0. Imagine that this is voltage, okay? When you apply the Fourier transform to analyze the spectrum of the signal, you will get this other curve, okay? And this axis is going to be voltage or power, depending on how you transform, but this axis here is frequency now. So let's say in general we can say that the distance from here to here is going to be the bandwidth of the signal, okay? In general. It's not an accurate definition, but just to you to get the idea, you can say like this. And actually there is another thing that will be important for later, that is when we do the same signal, let's say the same type of signal, but is wider in time, okay, it becomes narrower in frequency. This will be very important when we talk about these pulse shaping functions in afterwards. So let's say this tool is the one that allows us to obtain the spectrum of a particular signal. And with the spectrum we can calculate the bandwidth, and then with the bandwidth we know which is the minimum sampling frequency to fulfill this Nyquist criteria. Okay, and remember that this allows us to go back into this process. Okay, from these dots to reconstruct the other signal. Okay, so this was sampling, and then quantization. Okay, sampling. So second step was quantization. Quantization means we take each one of these instants in time, okay, but we still have an analog amplitude, voltage, power, whatever, and then what we do is put some quantized levels, and then we assign each one of these dots to these quantized levels. Okay, this is a necessary step to, let's say, to end this transformation between analog and digital. Okay, sampling, quantization, and then remember that we go from analog, we have voltage, whatever, to digital, we have bits. Okay, we have ones and zeros. So what is missing here, sampling, quantization, what is missing is we get this voltage that is quantized, and then we codify, for instance, with binary digits. Okay, if you know binary codification, you have a 4, then it's 1, 0, 0. Okay, this is the most used. This direct, it's called pulse code modulation. So from this we get the stream of bits. So this is how we finish the formatting block. So next block is modulation. So modulation converts this stream of ones and zeros, a stream of bits, to, as I said, a sequence of what are called symbols, which are complex value quantities, let's say. Okay. There are many modulation schemes. Okay. The most basic, let's say, or the most known one is the amplitude shift keying, which uses a number of amplitudes to codify these symbols. Frequency shift keying, which is a number of frequencies. Phase shift keying, which uses a finite number of phases. Qualitative amplitude modulation, which combines both amplitude and phase. And then there are more advanced modulation schemes. Basically, the modulator has two blocks. One is we got the stream of bits. So this can be whatever. A picture. No? You have the stream of bits. Then you group the bits, okay, like groups of 2, group of 4, and then you do this mapping. Okay, I will put now an example to understand it better.
an example that is PSK, that is this phase shift key. So this modulation is the most used in satellite communication. And this is why I'm putting this example, but all the others are valid. So imagine we have a sine wave, okay, that is the one we're transmitting. The most basic PSK modulation is called binary PSK, BPSK. Okay? In BPSK we codify. When I say we group the bits, we can take only one. Okay? We take one of these bits, which can be 0 or 1, and then we codify the 0 as this shape, and the 1 as this shape. Okay? This is called phase, because actually in a sine wave, when you change the phase 180 degrees, you are turning this. Okay? So this is one. Okay? This is the most basic PSK. When we go to higher order, let's say, we have this QPSK. QPSK means quadrature PSK. Basically, it has 4 different outputs. So instead of taking 1 bit, we take 2. Okay? So if we take 2 bits and each bit can be 0 or 1, we have 4 combinations. 0, 0, 0, 1, 1, 0, 1, 1. And for each one of these, we assign these different shapes. Okay? And so on. I mean, we can have 8, 16, whatever combination of this. But we will stick to these 2. And these 2 are the ones that you are going to see in the lab. But let's say this is accurate representation, but this is not practical representation. Okay? So a practical representation of this modulation is called constellation diagram. Okay? So we can transform this, which is this, okay, into something that is represented in a plane. Okay? Which basically it has 2 dimensions. One is called in-phase component, and the other is the quadrature component. That is simply when you take the real part of this symbol and the imaginary part. So we take here the real part and here the imaginary part. I said we codify it in complex, okay, complex values, and we can represent the complex value into let's say real and imaginary, or what is called in-phase and quadrature. And then when we have BPSK and QPSK, okay, we are representing them like this. This is BPSK, okay. So we have one point here, and the other here, and then let's say the phase between this and this is 180 degrees, as I said before, okay. And then QPSK, we have 4 dots, each one at 45 degrees, okay. And as I said, there are others. When we represent the APSK, you have 8 dots, 16, or you can have this on-off key, basically is 0 and something. You transmit nothing, you transmit something. These are other modulation, but I mean, I want here that you understand what is BPSK and what is QPSK. Okay? So, we talked about modulation that takes place into the transmitter, but then we have the complementary block, let's say, in the receiver, that is the detection block that undoes this modulation. So basically it recovers the bits from the complex value symbol. So let's say this detector, okay, has to decide which symbol, let's say, has to decide which symbol has received, and from this the bits are generated, okay, depending on which symbol has decided. So let me put you one example, and maybe you understand it better. This is what we transmit for BPSK. Okay. For BPSK, when you have a 0 bit, you transmit this. It is a negative quantity in the real axis. When you have a 1, then you transmit this. Okay. This goes over the channel to the satellite, goes back to the receiver, and the receiver receives something different because there is some noise, there are some what is called impairments in the communication. And maybe you transmit this and then you receive this. You transmit this and you receive this. This is an example. Okay? Basically you have an error. From here to here you have an error. Okay? And this error is the one that the detector has to decide which symbol has been transmitted before. But it has to decide it from the received symbol. So this happens for each one of the symbols. Okay? So then you transmit this, you receive it with some error, okay, around this. And basically when you aggregate all together, you can, let's say, infer that a good decision could be like whatever is in the right side of the y-axis is going to be a 1, and whatever is in the left is going to be a 0. Okay, this is one of the simplest decisors or detectors that you can implement. Actually, this is what we implement for a PPSK. No, so for a PPSK, this is called maximum likelihood detector. Okay, you say whatever is going to be received from this part, I assume that this was a 1, and whatever is in the other side, I assume that this is a 0. Of course, you can have an error, as we see here. Some of the red dots are in the other side, but this is something that the receiver has to assume, let's say, because you cannot know a priori. But this is how you implement a detector, and this is the process is used to undo the modulation process. So whatever you receive here, you put a 1. Whatever you receive here, you put a 0. For PPSK, is the same idea, but then you have 4 symbols. So basically, the 4 quadrants of the plane is the ones that you are using as detection regimes. So this was more or less everything about modulation and detection. Okay, and now I will talk to you about pulse shaping. So we modulate. We go from bits to symbols. Okay, and what happens is that these symbols, when you look the signal in the spectrum, is they are going to go by, let's say, a lot, much more than what you wanted, let's say, because you have a reserve bandwidth. You have to transmit in this reserve bandwidth. So then you use this method, this block, to change a little bit the shape of the spectrum, and then let's say fit your signal into the bandwidth. So as I was saying before, the Fourier transform allows us to analyze the spectrum of a signal. Okay, it's a tool that allows us to go from time to frequency. And then now I want you to understand like another feature of something that happens with the Fourier transform. That is that you have a trade-off usually. So you can have something that is very in time very limited, like I transmit now and start and finish. Okay, but then when you look this in the frequency domain, this is going to occupy a lot of bandwidth. Maybe the bandwidth that we can transmit is this one. Okay, so we have to do something to limit this. Okay, and then one can say, okay, let's do the opposite. Let's design some signal to occupy only a piece of the spectrum. Oh, this is our band to transmit. But then, when you go back to the time domain, what happens is the opposite. Is that I wanted to transmit now, but I'm actually the signal in time is occupying a lot of time. So this is a trade-off actually. When this happens, okay, this is called EC or inter-symbol interference. Okay, this is an effect of what happens in time. When you want to transmit something, you design in frequency to be very sharp, but then in time occupies a lot. So this means that, imagine I want to transmit a bit. Now I transmit one, but to transmit the other I have to wait like here. I cannot transmit before. Why? Because basically this one is occupying a lot of time. Okay? So then what we do, we try to find a trade-off. Okay? So we reduce the states in time. So let's say I can put the next bit in here, the next symbol actually, closer. But then I don't have this very sharp spectrum, but they have something that is called excess bandwidth, and actually can be modulated. So this is, let's say, this is how we try to design this pole shaping function. So whatever symbol we get, we try to we make an operation, okay, with these kind of functions to make them occupy a relatively sharp or narrow bandwidth with relatively short time function, let's say. So, and when I was talking about this, how we put the symbols here, this is very well known as the Nyquist-Ising intersymbol interference criteria. Okay, which are these conditions to be fulfilled to transmit one symbol after the other without interfering between each other. Okay, so we have this shape. Okay, we'll talk more about this shape in the next slide. So the condition to be fulfilled to transmit a symbol just next to the previous one is that in the maximum of this you have a 0 in the next one, okay, and this one as well. Okay, you look all the functions, when one has the maximum, the other have zeros, and the same occurs for the next one, and for the other one, okay. So this is the intersymbol interference criteria. If you fulfill this, then the communications will be good. So which kind of function we use as a pole shaping function? So this function, the most used in satellite communication is the square root raised cosine. Okay, it's something very important as well. It has this shape. Okay, basically it has 1 when you transmit, let's say, and then zeros when you are at the time, the symbol time. Okay, and then it has let's say a tuning parameter, which is this beta here. Okay, so you have to understand that you can tune this, and you can change this beta parameter, and then in time changes like this, okay, which doesn't have a lot of meaning. But when we look at the Fourier transform of this, the spectrum of this, then it has a lot of meaning. So this beta basically is tuning the portion of the bandwidth that the pole shaping function is using. Okay, when the beta is 0, we have this very sharp function. When beta is 0.5, for instance, this means that you have increased 50% more. If beta is 1, then you increase 100%. So you're occupying more bandwidth, okay, but then you can go faster, let's say. Okay, so this, yeah, I think this is everything I wanted to explain about the modulation and pole shaping. So you have any question? Okay. So in the lab during the next weeks, you will work on this. Okay. You will work not with the theory, let's say, because this will be given, and what to let's say apply this. You will implement this in LabVIEW. So in LabVIEW there is a very nice way to do this kind of signal processing things. Actually, one blocks. So you put some blocks like multipliers, summation. Then you have graphs. You can have controls and so on. And then you can see how, let's say, you can play with these things. You can evaluate how the system works, how a modulator works. You will see this in more detail. Okay, so then I leave the floor to Juan. You continue the next part.
Hello everyone. Yes, now I'm going to explain about the part of the transceiver impairments, mainly the synchronization part, and explaining what happens in a real receiver instead of what we expect ideally. So what are the actual limits of the satellite communications, and what are the problems that we are dealing every day in the design of receivers or the transmitter or all the part of the satellite communication, or also the payload that is also a component I suppose you saw in another course. So yes, as I said, there are different impairments that we studied before, but there is also some way to overcome them. Is what we call synchronization. That is to track the signals that vary on time and frequency and amplitude as well. So this is what we were going to discuss. We have the satellite link. Here, what we call this is the ground station. This is what I'm talking today. It's composed by the transmitter or gateway on the user terminals or the receivers. Normally with a smaller antenna than this. The other part that I'm not going to discuss today is the satellite, the payload. It is the one that Bhavani is teaching to you or will teach. Yes, so this will be the other part. So we're going to focus on this ground segment. And we have, for the uplink, we have one frequency and another frequency for the uplink, the feeder and the receiver link. And also we have the control link. That is the link that is used to manage the function of the satellite. Yes, we're going to focus. Yes, one of the main part of the and most costly part of the receivers and also for the gateway for the transmitter is the LNB. I suppose you know what is an LNB? You know?
No.
Yes. So this is the LNB is the radio frequency part of the communication chain. I mean, it's the main thing that you use to detect the signals at the beginning. So it is a low noise block, and it's the one that you mainly lot of time put in the front of the feeder of the antenna. So as you should know, you should put the low noise as close to the signal, because you put in a later stage, the signal will be already degraded. So normally in the commercial receiver, you put the LNB, and this LNB is the most expensive nowadays part of the system because it's a RF, it's an analog component, it's a bulky thing compared to the modem that is cheap, that is €1 each, and it determines the performance of our receivers. Here, one thing that is important is the phase noise for the receiver and the noise figure. The phase noise is how the oscillators that are regenerated in the LNB modify over time and drift and dance over time. This is a very important criterion or parameter. And
is it basically a low-pass filter? So
not exactly. It has, in fact, it has band-pass filter and low-pass filter at the end. I will put in the next slides. But the main thing is that they have low amplifiers, so that are at the beginning of the just close to the antenna to amplify the signal, because the power that comes from the lights is very low. And then the mixer. What is the mixer? Is the thing you going to say?
Yeah, so LNB is like the same as what we see as LNA, like low noise amplifier, or
LNB is the low noise block. The more important block of the LNB is the LNA.
Okay.
Yes.
So it has more things.
More things,
okay.
yes. Have the mixer, have the oscillator.
Okay.
And also for the transmitter, you need to handle a lot of power, because we need a lot of power to reach the satellite in the uplink, in the return link. So yes, it is a figure of the LNB. As you say, we have LNA, also low bandpass filters. Normally are resonant cavities or ceramic filters. Then local oscillators. Then bandpass filters. And here we generate some signal in the intermediate frequency. that are the ones that are collected by the modems. So, and with a good enough power. So this signal here is amplified many times, normally 60 dB or around 60 dB. Then the modem can handle a lot of noise, but the signal is in a good range. And in a frequency range that is translated to the one that the modem can receive. Yes, for that, what I said, the important things are more in the LNB than in the modem. Modem solve the problem, LNB generate the problems. And what I say, the noise factor or the noise figure of the LNA, and also what we call the phase noise of the local oscillator, how the oscillator moves over time. And also very important, the power that the power amplifier to reach the satellite can achieve. So for very expensive LNA, it can be 1,000 or more euros with very low noise figure, very low phase noise, but there can be 30 euro or one that we put in our houses to have the television.
We have two cards, one output and the other is output, but it seems that one, I don't know if this is a signal or some information that is.
Yes, it is for a modem. We need to receive the signal, and we have very slow amount of power that comes to us. So it comes to the LNA. In this way, this is the feeder. We put here the feeder, and we put the LNA normally in the feeder. I mean the feeder is the parabolic reflector. So this we call duplexer, waveguide duplexer, to divide both signals. Normally we can use the same duplexer because they are separated in frequency. This chain and this chain. Okay. Then here we receive our signal and we get the bit and reconstruct our information, and here we transmit our signal. So we can have two-way communication.
So if we have we just received the signal, is the low part will be retained?
The reception is this one, the LNA, the low noise amplifier, and the transmitter is the power amplifier, this part of here. And these two modems, maybe if you have seen the broadband modem, in the television you only have the receiver. But in the broadband modem you have two cables, one for transmit, one for receive. So one important part is the local oscillators, and the local oscillators are per se also control systems. Maybe some of you have notion of made in electronics. You know what a control system is? Someone else, you know? We know? Yes, it's a automatic loop in which you can track your desired parameter over time. And in this way you can generate a very precise signal. So a control loop is used to generate the oscillator signal. It's this sinusoidal way that we generate to down convert our signal. Normally it looks like that. We have a voltage control oscillator. It's a microwave device that generates kind of a frequency, let's say we can say 20 gigahertz, but normally this resonance circuit moving frequency is not stable. So what we do is that we compare to another more stable frequency, but in lower frequency. So what we need to do is to decrease the input frequency with a frequency divider. Okay, and then compare it and track the phase of this oscillator. Then, as you see here, we can use very stable frequency reference, crystal oscillators, or thermal control crystal oscillators, this will be more expensive. And also, in the end, if you want a very expensive receiver for special application, military, whatever, you can use also session clocks that are kind of atomic clocks to generate a very, very stable. Here it is the model of this very cheap crystal, but still it can be useful to track the resonance circuit and generate the local oscillator that is used to down convert our signal. So, of course, the signal that we generate with the clock have a very precise period that doesn't change over time. Very, very precise. So what we do with all this circuit is to put to higher frequencies. And of course, reducing these ugly Fourier transform that we can obtain for this. So just delta in one frequency. So in general, after everything, we should generate a sinusoidal that we use to multiply with the incoming signal in the LNB. So this will be the ideal. You see, but we did, and then this peak in the Fourier transform that Jorge was telling. So when you apply this to your incoming signal, what you do is what you shift your signal for the 20 gigahertz that we were talking to baseband, 0 hertz with some bandwidth. But in reality, it is not like that. We have like this. So because the amplitude and the phases and frequencies are varying, and the spectrum or the Fourier transform will look like this. So when we multiply this with our signal, everything becomes very ugly. So this will be our main problem, this part. So maybe in some way we can deal with that, but this peak should be narrow enough. Should be more narrow to preserve our information. If it's too wide, we need to find a way to track more in the digital part. So this means problem in the receivers. It's important to know.
Now, can you just repeat that from the plot, the graph?
Yes, sure. In the graph, yes, this is what we have in an ideal system. We have a perfect sinusoidal over time, and this is the Fourier transform that we have. If we have that, and we multiply this signal 4 by our incoming signal, what we do is that we shift.
I just want to know, like when you're saying Fourier transform, we just have a single frequency in that. Is that what you're trying to say? In the
Exactly. Just a delta Dirac, mathematically speaking. Just one point with a lot of energy.
Single frequency, one power we have.
Yeah, exactly. The total power is concentrated in
one frequency.
In one frequency. Then when we multiply this with our incoming signal, we shift. In the other case, we also shift, but also damage all our signal. It's not smooth. We damage a little bit, we convolve, is the mathematical operation that is happening. The Fourier transform of our incoming signal with the Fourier transform of the oscillator is maybe to give this detail what is happening here. So there are ways to measure this phase noise. Maybe if you're going to put into commercial receiver, how to quantify, how to model these things. And the way to measure this phase noise is compared to one side of the Fourier transform, or the spectrum to say in more clear words. So for every point, we give a parameter of the phase noise. Here, here, here. And normally it is given in logarithmic scale, but the measure of every point is the power in this area of 1 hertz to the total area of the plot. So this is the way to specify phase noise. And because it's a division, this phase noise have units of dBc over hertz units. It's a very important parameter. And it is a single-sided phase noise because only one side is taken of here. So assuming that all phase noise is in one side. Another important, very, very, very important thing of the oscillator of the normal phase noise is that they don't have constant phase. Over a long period, here we have 10 seconds, and it is radiance, it drifts. And if you continue to the infinite, it's continue drifting and drifting.
I just have a doubt. Like for example, in the previous slide, the one PSV versus frequency. So once we know that we have a f naught frequency, and that we are taking like a reference, then why not just assume that everything else is noise and all the power is located on this frequency?
It is a convention. And mainly, yes, the thing is that let me explain that. In a real system, in an ideal system, you say, okay, you have a delta Dirac and you can measure the power. So you say, okay, in which part you have your power.
Because my PSP that is having that is area.
Yes, but
PSP
in the
is
reality, you
total
don't have a Dirac delta that you can measure. What you have is an equipment that gives you the power of a big thing, of all. It's because of that. Because you don't have something very. In fact, here I draw very, very narrow, but it should be less. In some way, you cannot see when it is useful signal and when it is noise. It's like a blurry frontier. Okay, going back to this is an important thing, and is that it never stays the same. It starts to drift. This is how the phase varies over time. So when this goes over long time, you have a lot of variation, and then you do the slope from here to there. It means that you have also an offsetting frequency. So your frequency also moves, and this is the main thing that you need to track in the synchronization. That's the reason why synchronization is so difficult and it exists, is because it drifts all the time. So we need to implement loops that are control loops that are fast enough to track these changes. So here is a plot once again of how an actual thing is measured in a power spectrum analyzer. You see here that it's not easy to find the power here. It's more easy to find, everything in the plot. To make it easy, it is in logarithmic scale, so it becomes a subtraction of the power here and the power in the average. Yes. So now leaving for a little moment the LND, we can go to the model that Jorge was already explaining, and it is here that we have another PLL, but this PLL is different to the first one. I explained well what is a PLL? No? Yeah, maybe going back is this thing that is used to generate a local oscillator. Yes?
Yeah.
So this is what we call a PLL. Good. So here we have a single chain PLL or conversion, but here we have what we call IQ.
Just one question. The PLL, it has a loop to control this deviation in phase of the oscillator?
Yes.
So
the PLL does his best to keep this deviation as more as possible.
Okay.
But after, in the digital part, there is a residual drift that we need to compensate.
Okay, so if you come back like to the graph of the drift, so with the PLL, we should not have this drift.
It is after PLL.
Oh, after PLL.
Yes, after
okay.
PLL, we still have drift, of course.
Okay.
If we have open loop oscillator, open loop resonator, let's say, it will be incredibly higher.
Okay.
It should be in general, after PLL, we still have drift, but it's very much decreased.
Okay.
Good. So here we have the IQ converter, and it means that we generate two branches of the signal with the IF. Let's say in here we have around 2 gigahertz. At the beginning we have 20, we don't convert to 2, we have 2 here, but now we go to baseband. And here we have a pair of signals that represent a complex phasor over time. Okay? So we have what we call I and Q branches. It's something that you need to know. That occupies baseband that goes from, let's say we have 1 megahertz bandwidth, it goes from minus 50 megahertz to 50 megahertz, centered at 0 hertz. So that's why it's called a complex phasor, and it has two branches. Here we have finally the low pass filters and the PLL to generate the oscillator. Here also a PLL to the digital model. In the digital model we have a pair of analog to digital converters. So this digital information is fed into the modem to decode our bits. So these have also similar impairment, and is that we cannot calibrate that these branches have the same response. So maybe we can have with what they call IQ phase imbalance. So also amplitude imbalance and self-mixing or DC components. So instead of having this shape like that, everything that comes here becomes mirrored at the other side of the signal. And also we can have a very high zero frequency component that is like a leftover of the local oscillator, and sometimes can be problematic. And also the phase noise that can also damage this central part of our complex phasor. Yeah. So when we put these, and then ADC distortion, that is the nonlinearity that we can have when we put the ADCs. And when we sample our signal, yes, I was trying to show this. We are not getting a constant thing all the time. You see how it spreads and moves. So we cannot, you see? We cannot keep this as a constant, so we need to track also the moment in which we sample our signal to keep a constant spectrum in the digital part. So now I think I go to the synchronization part. And is how we use our signals to get these things synchronized. For this synchronization, one thing is that we can use the information or some part of the information that are known a priori to.
Maybe we can elaborate.
Yes, good idea. Yes, take some water.
The right time.
Yes.
So whatever little bit you understand.
I feel you right now.
Because when you are clearer, you are
Maybe as much signals.
Everybody has their subject work.
I know what you're saying.
But when we do, let's say, 3 so now we can.
He was trying really hard, this thing, let's grab it. Oh my god, what happens? Yeah, because I had to take this.
So sometimes you change the parameter of the gain of the loop. Okay. Yes, and now the next step, we need to put continuous acquaintance. In the resampler and everything.
Are you seeing
No.
I trace history.
Oh,
It's
I've
for-
seen.
Not yet, too soon.
Yeah.
But it goes faster sometimes. 16, 8. But it's for some this morning. Everything. In one example. And but 16 it is for a plot or in the host. Some problem in the host. Yeah, no, what is it?
To 4. Digitally is the same.
Yeah,
Just
but
that it might have
no,
noise or
no. In fact, when you go, let's say, to 2 mega samples, to 4 mega samples, or 8 mega samples, you work much better, much better. The peak of the vector, everything works better. The thing is that when we go to 16, it has some bottleneck in the host because of the plot, because of the
the blocks.
I can throw that we can go to 33 mega samples sooner or later. Yeah, because it's the actual thing, the PDA. Yes.
I mean, you can do one
Yeah. And the other thing, we other thing that we now have is the pilot. But now we have intra-pilot frequency calculator. It's a technology fast. But it is sampled by inside the pilot. You can compute the slope inside one pilot. Because you cannot do, I mean, it was very difficult to go from quadrilateral to pilot. I mean, pilot in the average of the phases of the pilot and compared to the next pilot because the aliasing of the phase inside from pilot to pilot.
I mean, what you want to say is the opposite. It's too much for the distance.
Yes. But we saw it. But we saw it.
But this if you increase the similarity.
Yes. we have kind of problem. We have just a bottleneck in the host, in the PCI Express. This is what we have. And the plotting.
This is because there is a very nice handoff in the quality. The quality monitor is able to reduce the frequency offset if you say enough, let's say, that everything will be understandable.
You see, but you see what is that, no?
To make the algorithm converge. So you can
sample rate, I believe that the problem starts to be like we have something that will have a lot of five force blocks, contours, just to debug. Okay? But this is the bottleneck.
yes, like the data is correct to the like you have floats.
Because you know, yes, you know that.
Yeah, but sometimes it's very easy. Sometimes we see that it's blocking the audio, so everything becomes.
It's like you have the computer, then you remote control this computer. It takes more resources, then it has not enough resources to process the audio, and then it throttles the operation of the computer.
Working
Yes.
I go for water.
then of course you have to test.
Yes. So, test, of course. As you said, you increase a little bit, then you have to tune the control loops for this new sampling rate. But to do this, you need these debug features.
You yes, you do that over. Just fine.
Yes.
The parameters that you need for that.
What I had before.
Then real stuff.
Part of the graph with the logarithms, which are arrows they divide the zero. So you know now start at 0, 0.222. Then the graph should go to
No.
the line was line space.
Yeah. Then just 0, 0, 0.
Doing something is still I don't know why you have black holes.
No, we don't.
We know that the fast. Yes, it's 1 year. Yes.
And then, the continuous operation, we put the second order into 100 megahertz. You see, then we start to put the steps in.
You might have this right after the step. And the frequency is if you put steps like minus 15.
Yeah, no, I think we should go there.
I don't want to.
internationally, or universally. These really radical types used to come barefoot. That took him a scolding, thank God.
So you are research assistant?
So what we do is we have like 4 combinations, 5 combinations. So at the beginning, only for the translators, then inter, then inter. Yes. Exactly. And after that, so we is the using the Bible, using the
Did you? No, I was going to finish informatics.
But I don't know
How to?
correct or not.
Do you have it? How open minded? Because I was doing LL. I think I'm done.
You mean the access 3?
The 3, yeah. The 2 I compared with yours and seems to be right.
I think the teachers gave us the book. We also need to update the D1 and D2.
Yeah.
Use the fancy.
Yeah, but I'll just see how.
I use the white in order to see
see
the
better.
yes. Yeah. And I show it was W, the last W, the last W1, and we use this was the times.
Yeah, I'll open. Yeah.
Okay. Everyone back? Yes. Okay, going back. So our difficult task, and it's what we do day by day here in the university for design of digital models, is the synchronization part. Then, as I was explaining, there are 2 methods. One is blind, and this is data aided. In the data aided, the green one we see here, it means that we use an a priori set of information that is a priori known to do our estimation. So we compare our signal, some period, some symbol, a set of symbols to a previously known sequence. Then we get a phase estimation, a frequency estimation, amplitude estimation, different, and time sampling estimation. And what is blind method or non-data aided method is that we just look into the signal without any a priori knowledge of it. So you just measure, let's say, the Fourier transform to measure the frequency, or the energy detector to measure the amplitude, or things like that, without any a priori knowledge of the symbols. Normally, blind methods for synchronization are less accurate and more slow than the data aided. Of course, at the price that we don't need to use some part of our time or our spectrum to send pilots. That's or these training sequences, preambles or periodic pilots. So what we need to do is to synchronize to get our bits. So we get our signal, we get the ADC. So we need to take back our symbols and recover our Netflix movie, let's say. But before that, we need to do many things. So first, frequency acquisition. It means that the frequency is not accurate, the PLLs, mixer, everything. So we need to acquire our current frequency in the digital part. Then One thing is that we are sampling. We are sampling the symbols, the two branches, as I was explaining, I and Q. But no, we are not sure that we are sampling the symbol at the current instant or the peak, so where the symbols happens. So we don't know what is the exact point where we should take this symbol and make a decision and put them into bits. So for that we need to do what is called time synchronization. And it starts with some kind of frame synchronization. So we have a long segment of thing or a long frame, and we need to start just where this frame starts. So it is very important to know where the elements of our frame are. Then the symbol time is what I was saying, related to the sampling. And after that, it can happen that the medium and the PLL and everything rotates our complex signal, our QPSK signal, for example. So we need to compensate that and compensate the phase deviation that I was explaining before in this only plot of how the phase drifts over time. So we need to track this frequency very, very good to have the point in the correct position. And it is very difficult, even more when you have noise on top of the signal. And then there is some things that are not exactly synchronization, but are very, very, very important for the works of the receiver. Amplitude rescaling. You know, when we have multiple constellations, the QPSK we have 4 points, but we have other satellite standards that have many points. We have to scale the amplitude of our complex value to the thing. So I say what is called AGC, that is automatic gain control. And then this fine tracking of this amplitude. And also one thing that is very important is to estimate how much noise our system has. Okay? From the signal. Mainly this can be done what we call the data aided. There are methods that use the pilot in the satellite standards and do this noise power estimation. And why is so important to know our noise in our receiver? Anyone has a clue? You remember when Jorge was showing that the error was some points close to the BPSK, another one is bigger.
Yeah.
Do you know why should be important? Because okay, if we have error, we have error. But rather than this, do you think why we need that? No clue?
To compensate.
In some way, yes.
A better function.
Yes, for the better function or some other idea. Do you think you know? Electronics?
Actually, I didn't distracted. I lost the point.
Well, so the thing is that it is important to know our noise, to report to the gateway, to our transmitter, what level of signal to noise ratio do we have, and they can change our constellation over time. Yes? And if we have the noise, they find the optimal point or the optimal constellation that we should receive to optimize the number of or data rate that we are receiving. And another related thing that uses everything is what is called channel state information. And it is how the phase and amplitudes are changed by the transmission medium. So it means when we know everything, we know our noise, we know our phase, our time, everything, we can have some clue of how the amplitude and phases change from the satellite to us, and also to give them to the transmitting to optimize phases and everything to what is called precoding. I'm not going deeper in that way. So this is the scheme of the receiver. Frequency acquisition, match filter, already Jorge commented. Frame synchronization is to know where the frame starts. Time recovery is where the symbol happens inside the sampled data. Phase recovery is an estimation. And then in the actual receiver is, instead of having hard decision, you say, okay, BPSK, we are in the left plane or the right plane. We can compute something like a probabilistic method, or say logarithm, like the likelihood, and it can be used for what is called LDPC decoding. So, in fact, you say when Jorge was showing that we have these two clouds that are together, you say, okay, you have a high probability that you will have an error. But when you compute, let's say, a frame, you can use this thing that can be very noisy to recover the bits perfectly. So this probabilistic detection, let's call soft detection. So here I have a nice plot of how is the frequency acquisition. Is something like what happened at the beginning. So it's like tuning a radio. So it's a control loop still. The go to where our frequency is. And as I said, there are non-data aided and there are data aided. Data aided is easier. Is for example computing the spectrum, and then we see, okay, if we do the FFT of our incoming signal and we have more power in the left, that more power in the right, we should move a little bit. So it is a control loop. So it has this frequency detector, a loop filter, if you are used to this, and no numerically controlled oscillator. So in that way, we give an initial guess of our frequency. But still, let's say here we have an error of 100 Hertz, and then we go to what can be 2-3 Hertz, but still not perfect. But this is our first thing. Then after that, we can go to the fine tracking of the phase. This is what I was explaining. It's a very easy method with the fast Fourier transform that uses the total power of the that's what's called PSD, that is power spectrum density. And then we compare these two areas and we create the error signal. That is the one that we put here to our controller. So there is also edge detector method. It means that we have with some algorithm also using being a non-data aided, we have some algorithm to detect the point where we have the edge. So at the end, what we do is we subtract this frequency to this frequency, have a rough frequency estimator that we need to go to another more selective method after. Yes, we show here. Here is a kind of sophisticated thing, also with the FFT, without the FFT, and is that we have these two filters. This is the match filter, that should have the same shape of the pool shaping. Okay, this one. And we have kind of strange filter, but when you multiply these two things, when you have positive values of the error when your frequency is too high, or negative values of this error signal when your frequency is too low because of that, because of this filtering. This is the filtering frequency. This was called quadricorrelator. We don't need to understand it very in detail, but just to know that it's a method that uses the match filter and this kind of strange filter, multiplies it and get an error signal. Next, it's also possible with data aided. Here I show you something from the DVS2X standard. It is the superframe format. And here we can, sometimes, for example, what we do in the lab is that at the beginning we have a blind method because the error is too big. But when we go to more roughly estimation, we can pass to, for example, in our case, to data-aided method. And here we use the pilots of the superframe. And here we can compute the frequency and phase differences between the pilots and track them. So we can do frequency tracking and phase tracking. For doing that, we do what is called a correlation. You know what is correlation?
Yeah.
Yes, it's more or less in some way it's a summation, and it's a comparison of how our a priori known signal is likely to what we receive. So in this way, we can have an idea of how the phase has changed from one point to the other, and try to compensate in a closed loop. And using this pilot, yes, that is a known sequence that repeats periodically. Yes, and for that, what is called sampling synchronization or sampling time synchronization is required to have better things. So then we'll go later to explain how this is like a complex system that everything is integrated. So it's like a circular spiral thing in which you improve all of your elements one by one. At the end, you get synchronized. So, you know, they say it's repeat periodically, but for doing frame synchronization, you need to start to find also a known sequence that is the start of frame. Here in the DVS2X standard, we have this sequence, known sequence is the start of super frame. And we do also correlations. Yes, here I show how this was what we should receive if everything is perfect, but we have phase offset, and we have this, so for doing the frame synchronization, everything is degraded. So for that, we should do the comparison in small segments, because if we do the comparison in the complete segment, everything is messed up. So we do the comparison in small segments, and it's what is called post-detection integration. That we do in steps. When we are synchronized, that everything is correct in phase and in frequency, maybe you can do the correlation or the comparison in the complete thing. Yes. This is the peak of the start super frame. This is something actual data that have been used in the lab. And when we do this comparison, this is our correlation signal. We do this estimation, and we have frequency drift. This is what we obtain. We don't know in which point of time our frame starts. So for that, we need to do the time tracking. Yes, when we put the time, the correct frequency, we should see a clear point. Well, so another important thing, you see a complex constellation here. You understand what it is? Could be a scale. But
numbers.
Yes, it is what we have after we have the famous IQ down conversion. It is what you see in time, more or less. And this is what we see in time as well, in the complex. So the signal go in time, let's say, do like this, jumps, between the symbols. You see, this is what we should see in the reality. So we get a sample at any time, let's say here. So we don't get exactly the symbol. We should sample exactly in the points where the symbols crosses exactly the ideal symbols. And it is not all the time. So it goes like that. And you take this out of your ADC. Okay, where do I take my sample? We don't know. You see? So we need to get the instant timing where you get your IQ signal and sample it. And it changes and it drifts because also of the phase noise that is giving the PLL of the clock of the ADC. You see? So for that we need to check the ideal timing instance. Here, how do we look the thing when we have some error in timing? we sample perfectly the time, that we always get this point, always. But if we have some percentage of drift, that we sample a little bit, let's say if it is here, the 0.7 whatever, the point, and if we sample a little with a little object, we get some image like that. So it degrades. It looks like noise, but it is noise. It is not noise. It is some sampling error. You see? And you have a signal that have perfect signal, no noise. But if we don't sample in the correct time, it is what happens. Okay? Then if we have this, let's say, what can we do? For example, how do we introduce, we need to introduce kind of a shift or an offset that is less than one sample. So it is not true that you can put a fraction of the sampling time, just taking one sample or the other. Okay? So for that, the sampling, the question is, what can we do to recover and go to this point? And the Nyquist sampling theorem says that we can recover any point of our waveform if it is sampled sufficiently at sufficient high speed, that is 2 times the total bandwidth. So in theory, we should be able to recover these points, and it is using by a kind of a digital delay. So it's a kind of filter that introduces a delay that is less than one sample period. Okay, I think it's clear, no? So it is known like a resampler. See, you have a timing error, and then you put to this delay filter a coefficient that gives a constant delay. Okay, and it's called also a resampler. And here it should be a control loop for implementing the time synchronization. Okay, so we have what is a sampler. At the end is kind of a filter, digital filter that makes it like a different coefficient that ponderates a previous version of the sample and generate a new one. It can be implemented in the finite impulse response filter. Maybe you know about this. Maybe no. Then you measure in some way the error and implement also a control loop. And then you do a loop filter to control this delay and put some coefficient of this filter to the resampler. So this is what I said before. For data-aided method, you can have this pilot, and then you can track the phases of your.
I have a question. Can we just go back 2 slides where we were talking about effects of timing errors? 0, 3%, 6%, 9%. Yeah, this slide. So when we are talking about errors, so what exactly with what are we comparing? What is the error?
Okay, it's a percentage of the symbol time. Let's say we have 1 megahertz, so the symbol time is 1 microsecond from one sample to the other. Okay? So here 3% means 3% of this microsecond.
Okay.
Okay?
That's an error. We are making a mistake in the
sampling time, in the sampling instant, where we take the. Okay?
No.
It's a percentage of the symbol time.
No, I understand that. What I'm trying to understand is what is our reference time? I mean, what is the correct, how do I say I'm on time, basically, if I'm having a 3% error?
Okay, how do you know? It is obtained by the timing error detectors. It is a way to know if I am sampling our signal correctly. Okay? This is maybe we don't have to cover in these 45 minutes. But yes, there are hundreds of methods, many methods to know, to detect.
No, maybe I think my doubt is more basic. It is just that I'm trying to understand when I'm talking about timing, synchronization. It's about matching our sampling along with the frame. Is that not what you're trying to do?
No. With the correct sampling instance. With the frame is big synchronization. I mean, from time synchronization, for frame synchronization is that you know where the element of your super or your frame or whatever are. I mean, you detect this thing, then you know, okay, from here to here we have data. From here to sample 1000 to 1000 plus 36, you have this pilot. Here is to know this other part, other kind of pilot, and this is some control messages.
No,
so for that, what you do time frame synchronization is that you know where the elements of your frame are. Okay, this is frame synchronization.
Like just for my understanding, in a CD we have like a digital, analog. It's in analog form, right? When we are playing it from a CD. So let us say I want to let us say a recording, a magnetic tape recording. I want to convert it into an MP3, so that is a digital conversion I'm doing. Now let us say I have a timing error of 3% or 4%. Is the song going to sound different? What is going to happen? That is what I'm trying to understand. Like, is it going to skip the words? Did you understand my question?
Yeah, but this.
Isn't it going to be distorted because it's aliasing?
Yeah.
Sorry?
Isn't it going to be distorted because there's aliasing?
Yes, you don't. In fact, when you sample when you sample, let's say here, what happens is you don't have all information, or your symbol is kind of a combination. It's intersymbol interference in some way. Because here, let's say, I am here, I start here, but I am going toward here, let's say. So if I sample in this corner, I have some kind of a linear combination of my symbol that is decided to the next. So that's what's called intersymbol interference. Yes?
Okay, maybe I'll come back to you. You can progress.
Yeah. And in fact, if you want to know about the timing error detector and everything, and I will be happy to help. Okay. Because maybe I suppose you're going to need that for the labs. So yeah, it's important. So here we will go phase. Yes, finally to end up, to finish this part, it is some kind of algorithm to implement from the data aided to implement what is called SNOR algorithm. That is a way to measure the signal to noise ratio of our receiver. So how it works? It works in one way. In one part, we estimate the total power of our let's say one pilot. So here we have total power. What it is computing the square and making a summation. Very easy. Okay? And from the other part, we compute kind of the correlation or comparison, let's say, of our signal with a known sequence. So, and then if we subtract the total power to the power of our comparison, we should have more or less what is the noise. And in this way, we can report our noise and receive the perfect constellation. And also, they give more power or less to be sure that we receive correctly. Okay, thank you. It is over. As I said before, if you need some more help or more details on the methods, I will be available. You have my information. Thank you very much.
Thank you.
Thank you, Juan. Okay, let's continue with the last part. So for this course is about communication channel, specifically related to satellite communication. I'm not sure which courses you already attended so far, but probably there was something speaking about channel, I don't know. Here it's more, what I'm speaking about will be more related to how you want to, let's say, design and model different part of the communication channel so that you want to replicate and do some, for example, simulation with satellite communications. Okay, the three main parts, first of all about communication and the impairments that you have on the channel that you want to model, you want to investigate on. Then about channel estimation and equalization at the receiver, and then some impairments affecting precoding. Here I have to ask, I knew that there was a class about precoding. I'm not sure it was done. No?
They skip.
Okay, fine. So let's see with the time. If we have time, we will also do this part. If not, we will skip. Okay. So let's start with the basic block scheme about satellite payload. This is just related to the payload. Then we will see the communication channel entirely. The objective, as I said here, is to understand how to model this channel and how to build, for example, what is called a channel emulator. Because this is what you need to test your technique. I don't know, you want to develop a technique and you want to test it. You don't have a satellite unless you're not SES or others. So you need to implement a channel emulator. And this is how and what you want to do that, and which are the main blocks you want to model to see the characteristic of your communication channel. This is what is called the bent pipe payload. It's called like that because this is fully analog. Here we don't have digital part. All the components are analog components, and here we are relating only to the payload, not on the bus. So from, let's say, block scheme, starting from the receiver antenna. The receiver antenna you want to model as the antenna pattern that you might have available from vendors or from literature or from whatever. And so this is what is the antenna pattern, how basically you get your signal from different directions, which intensity are those signals that you receive. Then you have a wideband filter. This is just a filter always in communication scheme. When you are receiving something, you put a filter because you want to filter out the noise that is not in the band you want to work with. LNA, low noise amplifier, as one explained, this is the same concept of the receiver applied for the satellite. You need a block that amplifies the signal coming from here because, for example, looking at the geostationary satellite, it's 36,000 kilometers far, so the signal that you receive might be very, very low, and you need to amplify it, but you want to amplify it such that you don't put a lot of noise inside. This is what is doing that. Then you start to have different, let's call those communication chains. So it will be different branches, because you might have different carriers at different bandwidth, and that's why you're splitting those in different parts. So you're receiving this signal, for example, in KA, let's say from, for example, 30 gigahertz, because this is the feeder link, and you have to reach the KA in the user link, so to the users, that is 20 gigahertz. So what you need to do is a down conversion from 30 gigahertz to 20 gigahertz. And this you do for all the different payload chains. Of course, the center frequency of those guys should be the center frequency of the carrier of interest. So you are shifting your spectrum, and then you want to filter out the other carriers. This is, then we will see let's say, the different blocks. Now it's just to give you a general idea of those. So then we will see block by block more or less how they can be modeled. This is called IMUX, input multiplexer. So basically you are selecting the carrier. Maybe I'm using the word carrier. Do you know what is a carrier? So it's like your signal of interest that has kind of bandwidth. So Juan and Jorge explain you what is a bandwidth. You might have different of those carriers for different channels. Whatever it's Canal Plus, RTL, I don't know, different channels might have different carriers, and those are placed differently within the spectrum, and you want to redirect those in these different paths. Okay, so you filter out what you don't need and you keep the carrier that you need. For example, here is going the canal plus, let's say. Then you have the channel amplifier, of course. You are receiving something from here that, depending on the condition, there could be rain fade, there could be other impairments that put down the signal power. So you need basically a component that prepare the next component, which is the high power amplifier, to amplify the signal, because maybe the level of the signal is too much low or it's too much high, and while instead you want this guy to drive the power amplifier at an exact level. This is what it is, basically a preamplification, yes?
I have one question. What the difference between LNA and HPA? It's
This
both
is,
amplifiers.
This is, it's right, but this is low noise amplifier. So usually when you have, let's say, block scheme in which you have different components, you want to keep you want to add as low noise as possible at the first component. So this is not a power amplification, a real I mean, here we are speaking about to amplify something of 200 watts, for example. Here not. Here it's a pre-amplification as well, let's say. It's not a real power amplification. You're not putting the real power here, you're putting the real power here. Of course, then those have different characteristics because of that, but have different roles, let's say, but are oral amplifiers, yes. So this is, as I said, is a pre-amplification, and this is the power amplifier. Here you're putting the most power that you have. So basically this is what, for example, consume, not all, but let's say, that consume most of the power on board. And then you are putting what is called omucs. It's another bank of filters. So this is done because you don't want to interfere with the adjacent channels. And this power amplifier might amplify also the non-linearities generated inside. We will see afterwards. So here you might generate some unwanted signals, let's say, and you want to filter out also those. And so this is the omucs, and then you have the transmitted antenna as well as before. It's related to the antenna pattern of the antenna that you're using. This is the basic model. For example, now you want to model a communication chain, and this is, for example, a reference from the standardization. You will have also class, I think, about standardization, which is called the DVB, which is digital video broadcasting. And here, basically, they suggest you what are the main block scheme or the main blocks you want to model to replicate a certain satellite channel. So, for example, you start from the uplink. This is the uplink, and you might have different uplinks because you don't have only one gateway. You remember yesterday you saw a lot of antennas. For example, it was not yesterday, sorry, last time. So each satellite might receive a signal from different gateways. So that's why you have different chains that transmit to the satellite. You have different impairments. One, for example, here is delay. So this, we come back probably to the question of the guy to one, why you might have difference in delay or timing error or whatever it is. You have an independent source that has its own clock that transmits, and an independent receiver that has its own clock that receives. Those two clocks are not synchronous. And the asynchronicity between those could be minutes, could be microseconds, could be whatever. So those two are not aligned, and you don't know. Unless you have a reference clock, GPS or whatever, but usually it does not happen, you don't know. They are completely independent. So when the receiver or the satellite receiver, let's say, start sampling it, for sure will not hear the right sampling instant that Juan was showing you. The peak, for example, of the waveform or whatever. And this is the error that you have. Here, the error is because you have different gateways separated completely that maybe can be also not synchronous. Also, the path can be different depending on where these gateways are positioned in the earth. And this is the delay that you might have from the carrier transmitter from here to the carrier from here to the carrier from here. So you have a time difference between those three. You have also frequency difference because you have a local oscillator in one gateway, you have another local oscillator in another gateway, you have another, and they are independent, if not driven by the same oscillator. And since they are independent, they might have different frequency. I mean, does not mean that they are transmitting one 30 gigahertz, the other 40 gigahertz. No, they are both at 30 gigahertz, but maybe this is 30 gigahertz dot 0.00001, this is 30 gigahertz dot 0.0002. It's a matter of precision of the components that you're using. That's why you have this small mismatch. Okay, from the satellite point of view, you see that the main blocks in a bandpipe model are the IMUX, the filter, input filter, power amplifier, output filters. These are the main blocks when you want to model a scheme. Of course, if you want to be very, very precise, you want to apply also other components, but these are the main ones. Then you go to the user link, and you have here is called the Allison transponder interference. So you remember we have different chains, and then these chains are transmitting to the earth, and basically you might have a small overlap between one and the other, and this is for you is an interference, and this is an interference that it's not coherent in time and in frequency, and this is how you want to model. So here you apply a delay, different delay from this, and then you apply a frequency mismatch between the two. Usually when you want to apply a frequency mismatch, you multiply your signal times exponential of j to p f, which f is the frequency that you want to apply, t. Then you have cross-pole interference. So usually when you transmit with what is called color reuse. That basically you are splitting your spectrum, but also you are taking advantage of the fact that you can transmit with different polarization. Can be linear, can be circular, but you have basically your signal are modulated with different polarization. Since components are not ideal, you might have cross-polarization, meaning that part of the signal transmitting in one polarization end up in the other polarization. And this is, of course, interference as well for you. It might be very, very low, but still, for some application, it could be important. And this is how you want to model it. It's always the same scheme. You see, it's similar as this one. It's exactly the same. Are just the values that might be different. But how to model that is the same. And then you go to the user receiver. Another important factor that usually people does not consider is the addition satellite interference. For example, you have a satellite at the geostationary orbit 5 east. Means 5 degrees east is the position of the satellites that you see. You have competitors that maybe have satellites are 7 east and at 5 east. So plus minus 2 degrees of difference. Those 3 satellites maybe transmits at the same frequency and at the same time. This can happen. So, of course, what happens is that what you receive is interference from that side, from 7 east satellite, interference from 5 east satellite, and how you can deal with that, basically, thanks to the fact that at the receiver, you remember you saw the dish of the receiver when we went to the NOC Thanks to that, basically your beam, what is called a beam, is a very, very steep beam. And so when you have a signal coming from +2 or -2 degrees, you have what is called a discrimination. That might be 20 dB, 30 dB, whatever, that put the adjacent signal down, let's say. But still, for some application, this is also important, and this is how to model it. You put adjacent signal interference as noise, basically, at your receiver. This is the version of the DVB. Yes?
You already had in this group that there is an organization that allocates some specific frequencies and bandwidth to specific companies to be able to use that specific frequency.
You might do this, but sometimes this is one way. So basically, you do FDM kind of. Some services take this portion of the spectrum, some other take this other portion. But there are some services that require the full spectrum, and all SES, Inmarsat, Eutelsat, whatever, are transmitting in that bandwidth at the same time, and that's why what exists is called coordination constraint data. In the coordination constraint data, basically it's an agreement between satellite operators, and in this agreement, basically you say each of us can transmit at maximum this, it's called AFPSD, but let's say at maximum this power. So that if you don't go above this power, you should not cause a lot of interference to the other services. It's a matter of coordination, because if not, it's like we are in a room, every of us start shouting, and nobody's listening. That's why it's convenient for everybody to have coordination constraints level.
About this timing thing, actually,
yes.
Basically what I understood is that when, okay, it's something like this, when, let us say, one satellite is transmitting bata, like this, BATA, BATA, BATA. But if I get the timing wrong, I'll be reading it as taba. Because you miss the 2 and then you start from T instead of reading from B.
Yeah.
But can you not encode like a stop or something so that you know the timing exactly, like bata stop, bata stop, bata stop?
So, yeah, I understand you want to make an analogy now with audio signal or something like that. So in general, let's say, even in audio right now, what happens is that you codify as bits, then you put bits in symbols as one in Jorge showed, and then this distortion you have at signal level. So if you have an error, what you have is just basically you have your frame which is not correct, and you throw, and you want to retransmit or whatever it is. Usually you don't retransmit on satellite, but okay. Or it's well done. I mean, the satellite, the signal that you heard, that is a proper one. But what happens if, for example, let's assume this audio signal, analog signal, and you sample at not the right time, and you want to listen? Probably what you have is, as one show in his slides, just you will hear noise, because you, instead of having perfect points, you have clouds. Clouds means noise. Like if I have to say, it's something like shh, something like that. If you want to translate in some kind of signal, audio signal, let's say. So this is what it happens basically.
One more thing about this uplink and downlink.
Yes.
So the frequencies are already different.
Yeah.
For uplink and downlink, but then you, I think, also use different planes, right? Because one will be vertical, other will be horizontal for the uplink and the downlink.
Different sorry?
For the uplink frequency.
Yeah, they are different, as you correctly say.
The frequency is different, but the plane also you are making it different, right? You have a vertical one, and then you have you use different polarizations for the.
Yeah. You can use different polarization also for the uplink. They are transmitting, of course, they are a different. There are more than one reason why you are transmitting at different frequencies, the two.
Yes.
For one, which is very, very simple, but you don't want to have self-interference from your system. Second question is that So the atmospheric attenuation depends on the frequency that you're using. And usually the higher is this frequency, the higher is the attenuation due to atmospheric. Whatever it is, rain, gases, scintillation, whatever it is. So in the uplink, you have the gateway. The gateway is a single object. It's not like users that are a lot and spread it over. You have a single object. You can use a very, very big antenna, meaning that your ARP, your power is very, very huge. So the uplink you care less because you have ways of transmitting more power if in this path you have a lot of attenuation. While in the downlink it's different. In the downlink, it's the satellite that has to amplify. And the only way the satellite can have power is through solar panel. And actually, most of this power is not even used for amplification. It's like, sometimes it's like the engine of the car that you dissipate heating, something like that. So for nothing, basically. While in the downlink, so you want to protect it. That's why you're going to a frequency which is below. Sometimes you also hear people saying you do that because the free space loss in the downlink depends also on the frequency. True, but half true, because also the satellite, the receiver dish gain depends on the frequency, and this compensates the two stuff. So it's more because of attenuation, atmospheric attenuation, let's say, and self-interference, let's call it. So we saw the DVB version. Now we see, for example, a manufacturer channel emulator. This is taken from IZT, is called the company. The model itself is called C3040. And this is a satellite link channel emulator. So let's, for example, start from the payload. From the payload point of view, you see more or less you're modeling the same stuff. There is only one more stuff, which is the phase noise. So it's a bit more accurate than the other, because you're also modeling the phase noise that you have at the satellite. But let's say, as we said, it's more or less the same. Then you have uplink components and downlink components. So if you really want to design a channel emulator, you take this block scheme, you start from the first, and you put your program, you start implementing block by block, and you have your channel emulator. I can just mention what are those stuff, but I mean, we don't really have to go very, very deep because I'm not an employee of IZT. So here is just to say that, let's say, you can replicate delay. This is, we understood what this is delay. Then you have Doppler. I have a slide about Doppler, so right now take the word just as it is. Ionospheric attenuation, this is atmospheric ionospheric attenuation. You can have shaped noise, or you can have arbitrary waveform generation. So you might want to put inside noise, like white noise, or colored noise, modulated noise. Payload we spoke about, downlink, as well as the uplink. You have ionospheric attenuation, you have Doppler, you have fadings. These are all atmospheric attenuation part. You might have also interference that you modulate with white noise or with arbitrary waveform generator. Then in thermal noise due to the receiver, and then you go to the real implementation of your receiver. This is how this IZT model the channel emulator. So we saw block by block. We want also to see what are, for example, a list of possible impairments. This is very, very general. It's not that all your payload implementation will have all these impairments. It's just a list, maybe not even exhaustive list, of all the possible impairments that you might have. So, for example, we start from the feeder link. As we saw in the IZT model, the Doppler, you can have rain fading. When it's raining, you have attenuation. atmospheric attenuation, time delay, and interference. We are resuming basically what we saw from the different models, from the initial one, for the IZT, and from the DVB. Receiver sensitivity, this is a matter of the sensitivity of the receiver of the payload. Then we go to the different block inside each payload. You might have frequency error because this is a down conversion. So a down conversion means that you have a local oscillator inside, and this might have a frequency error, and phase noise, as Juan described. Then you have filters. So being a filter and a not ideal filter, you might have different frequency response, which are not ideal, not flat, for different group LA. And you might also have what is called Allison satellite interference, channel interference. So carriers that are close to each other might interfere. You put a filter, yes, but the part of the bandwidth that is inside your bandwidth that you cannot cancel. This remain, and this is interference for you. Normalization of the amplitudes, which is basically the preamplifier, nonlinear distortion of the amplifier, the same effect of the filter, and the downlink part as well. This is just basically the resume of what we saw so far. So we spoke about bent pipe payload. Here it's more flexible payload. Let's call it also digital payload. So more recently, let's say satellite manufacturers starting building this kind of payload. Not anymore everything is analog. Now you have also digital capabilities. What is the advantage? When you launch a satellite, then the satellite is as it is. You cannot change. Those payload change, amplify this carrier, then you have another carrier, you cannot change about the carriers, and you cannot do much with that. While in this kind of situation, you can adapt. You have the flexibility to adapt a lot of stuff like carrier sizing, like pointing direction, even a beam pattern as well. How? So let's say first part, okay, it's very, very similar. This is just, let's say, the front end part of your satellite. Then you start having down conversion. This down conversion is not anymore that you want to go from 30 gigahertz to 20 gigahertz. No, you want to down convert to maybe baseband, maybe IF, depending on the different implementation, so that you can transform your signal in samples. So we are going to the digital domain here. This is analog digital converter. We transform the signal into digital, as Juan and Jorge showed before. Then we have what is called DTP. So basically, it's can be an ASIC, can be an FPGA. It's a kind of processor in which you can implement your firmware, your code. And basically, what you usually implement here are filters, channelization. Channelization, it's basically because you have the flexibility. For example, you have a carrier here, but you want to transmit here. So this is kind of doing, let's say, a switching from this part to this part after filtering it. And then you have also beamforming. So you apply weights to your signal, so that this is a technique that basically change the beam pattern shape, let's say the shape of your beam pattern, and can point a beam towards one direction at one time, another direction another time, depending on the demand, on the traffic demand. Okay, here we are digital, then we have to go back to the analog component, and same as before, we have to come back to, for example, the 20 gigahertz of the K band in the downlink, high power amplifier, and then transmit antenna. Of course, when you implement this kind of chain, you might have other impairments, which is quantization noise, filter imperfection, fixed point operation that you have inside the DTP, and the quantization error. Okay, let's see one of those. Let's say, just to have an idea, I try to put basic stuff to explain. Let's first start from the Doppler effect. So this is, okay, it's a nice picture that we found on me that explains how the Doppler effect works. first of all to say that it's basically an effect that you have when you transmit a carrier, and you have a different velocity between the transmitter and the receiver. So you see, you can experience the Doppler effect every time there is an ambulance passing, because what you hear is the frequency changing of the alarm of this ambulance. This is because suppose you are transmitting this sign, this signal here, and look at those circles like the peak part of this sign. So this is, for example, this circle, this is this circle. If the ambulance is moving towards this direction, what happens is that basically your wavefronts are kind of compressing, as you see here, and as you see here. But when this happens, you see that the frequency changes, which is higher frequency, as you see from here. That's why you have this Doppler effect, basically. This happens with the electromagnetic waves, also with the audio waves, because here, in fact, we are doing the example of the ambulance. Basically, what creates is what is called Doppler shift and Doppler spread. This is a general formula in which the new frequency is given by the original frequency. This is C is the, let's say, light, the velocity of the light, and this is the velocity of the receiver and the velocity of the transmitter. So maybe your receiver is the velocity is 0, the transmitter is something, etc. So you understand that for geostationary satellites, that for you it's like a fixed point in the, let's say, in the sky. The contribution of the Doppler is less significant. I didn't say it does not exist. I said less significant because usually it's in the order of 100 of hertz, like 100 hertz, 120 hertz, something like that. Because still there are some small movements on the satellite. Of course, you see the effect much more in the Mio constellation or Leo constellation. We spoke a lot, I remember, during in SES about Leo constellation as well. So you were discussing about two challenges, I remember, of Leo constellation. This is one of the challenges, for example. Also trying to find algorithm to compensate the Doppler. Right now, for example, for Mio constellation, or let's put like this, for stable orbit Mio constellation, you kind of compute knowing the orbit of the satellite. Knowing the orbit, knowing the position of your terminal, you might to some extent understand what is the Doppler level, and you compensate. Frequency offset, okay, I don't go through this because one also spoke about that. Phase noise as well. Maybe just to say, if you want to implement it, this is a block scheme how you implement it. You generate with the Gaussian distribution random numbers. Then you go to the frequency space, you apply your mask, the mask, for example, that one showed to you. You go back to the time domain and you have your phase noise that you have to include to your signal. These are, for example, in time, what you see as a combination of frequency and phase effect. So this is phase noise. It's called noise because you see it's kind of not really modulated kind of error that you have. And then you have frequency. And frequency for you is kind of a ramp in the phase, let's say, phase time graph. Okay, now we see IMUX-OMUX filtering. Those are the filters that we have at the satellites, and we explained why you need some filter. For example, is to separate for the IMUX the different channels. Those are the response. So this is frequency. So for example, you have a carrier here, and this is how it's filtered. So for example, if you have a carrier here and a carrier here, this carrier is attenuated because you want to select only this one. Because basically what you do is multiplying in frequency the spectrum of your signal and the mask that you see here. And the blue is the frequency response, the amplitude, and the purple is the time delay, because those kind of filter might also generate a different distortion in time, which is called group delay. This is how you want to compute the group delay. It's basically a derivative of the phase component, the phase response. This is from the IMOX, and this is from the OMOX. Those are in scale, so you can see basically that usually the OMOX is, let's say, the in-band part of the OMOX is smaller than the IMOX, because when you transmit, you want to really be sure that you don't have adjacent part of your carrier, and you want to eliminate those. So this is why, so basically it's the less as possible, at 36 megahertz. Non-linearity, then we go to the amplifier, TWTA, SSPA, whatever. This is the high power amplifier. It's what gives you the power to the signal that you want to transmit. So those are called IM-IM and IM-PM characteristic of your TWTA, of your power amplifier. How you should read this? So this is your saturation point. So basically, let's say the maximum amplification that you can put when you consider a continuous wave signal. And so your signal, your input signal arrive here. This is the characteristic, IM, PM, and the output signal is basically mapping the input toward this function to the output. So in power, you have, for example, a signal which is a point, for example, a sine wave, which is not entirely a point, but more or less. And you go here and you go here. You can reach the maximum. While if you have a modulated signal and your input power range of your signal, it's like a small segment, let's put like this. So for example, this for -2, -4, you reach this point, you see the signal is very, very shrinked because it happens a distortion to your signal. I try, let's say, to explain very intuitively without formulation how it works. This happens both in power, in amplitude, and in phase. This is what is called typical, this is also taken from the standardization, typical K-band TWTA. This is the linearized TWTA. So this guy here produces a lot of distortion. This guy here produces less distortion. Why? Because here you see it's a very, very straight line until this point. This is what is called the linear region. When the region is linear, you're not distorting anything. Here instead, you see it's like a curve. So even here, even if you're working with the proper input power, you are somehow introducing a bit of distortion as well. This is only in power, then you also have the same things in space. Yes, it's time.
Yes.
Really?
6.
Okay, this is effect intermodulation. Okay. Beam pointing error, I don't explain. Predistortion, yes. This is a predistortion and equalization are more or less the same part. I want to start with this to show you what is the effect. So basically, when you have nonlinearities and you are transmitting, for example, the points that Juan and Jorge were showing you, the effect of nonlinearities is not only that you have clouds, but you see those clouds are kind of distorted and not really a circle, are very strange stuff. And also inner ring and external ring are like shifted in phase, because you see also you have a characteristic in phase. So this means that if you try to recover this at your receiver, depending on the level of the distortion, you might not be able to do that. So even either you put more back off here, so you have less distortion, but more back off means also you transmit less power. This is the trade-off. Okay. then when you recover the constellation, it should be something like this. Usually to understand what is the optimal point, you recall to what is called the total degradation. So you want to understand what is the degradation depending on your OBO, on the backoff that you apply. You cannot, as we say so before, it's not it's a trade-off. It's not something linear. So if you reach 0, you have a high degradation. If you put a lot of backoff, you have also high degradation. You have to reach a minimum point, which is the optimal point. Okay, equalization. This is very general. Actually, I found this picture. I don't remember where. Probably MATLAB will help. Just a very, very basic how to categorize equalization methods. There are adaptive equalization of maximum likelihood. Maximum likelihood usually use what is called the Viterbi algorithm. Adaptive filter, there are different kinds of implementation, for example, least mean square, recursive least square, and custom modus. What are very, very important in the design are those 4 parameters, because if you want to compare the different representation, you have to compare on those 4 elements. One is the convergence rate, how much time it requires to have a good, let's say, behavior. The computational complexity, because this is something you have to apply at your receiver, so computational complexity is important. Residual error, because some can be very, very fast, but the residual error is very, very high, and the sensitivity to the quantization errors. End-to-end system, just to show you where the equalizer is it. So this is what one showed you before. The RF part, the terminal part, when you have the RF front end, the filter, and then you apply the equalizer. Linear equalization, this is a general scheme of linear equalizer, and if you speak about zero forcing linear equalizer, what you basically want to do, you see from the formulation, you want to invert your channel. So, how to explain this intuitively? Basically, your channel applying a kind of distortion, which might be it increase the power by a factor of 2, and you don't want it. How you do that? How you can apply equalization? Basically, you put 1 divided this power of 2 to have at the end what you wanted to have in amplitude of 1. It is very, very intuitively. Then there are different formulation, because you don't have just a number, you have a kind of finite impulse response for your channel. But this is more or less what it happened with the zero forcing linear equalizer. Then you have adaptive equalizer. So in adaptive equalizer, you have your channel, which is unknown, and this is what you want to estimate basically. And this is your adaptive filter model. So here you're trying to represent basically this guy, because if you know this, you can basically invert it and remove it. And this here you have an algorithm which basically model the tap, the weight of this finite impulse response here. How? So this is the signal yn that comes. This is the one that you reproduce. You want to minimize the difference between these two. And this is what is called the error function, and the error function is what drives the design of the adaptive filter. And then you have LMS or LLS, whatever. This is, for example, the example of last mean square. With the LMS, you are adapting all the different tap or your finite impulse response that you want to reproduce, and this is the algorithm to do that. So apart from the initialization, you calculate the filter output, you compute your error function. Your error function towards a step size is what drives the updates of your delta coefficients. I think I finished. So this was the last slide. Since you didn't do anything about recording, there is no sense to go ahead with that. And thank you, everyone.
Thank you.
Okay. One last thing for Thursday, for the lab. You will work in pairs. So if you can already find your couple.
Professional. Some of you have the key.
Oh, here.
Thank you. So we have 30 minutes.
Yeah. It says we have to create a code that compares the temperature Fahrenheit and Celsius and tells you the photos. Yeah. How do you make it so that because it needs to be exact, precise to this 56 decimal digit for it to become always equal?
Yeah, so you just, instead of saying equals, you make it some epsilon. So you say that it's equal if the difference is 0.001 or something like that.
Or it's the 1 minus the opposite 0 and 0.
Or instead of saying you put if the difference of these two is less than 0.0001.
Yeah. No, that's not the problem.
Yes.
So that puts, so what I do is I put the Fahrenheit.
Okay.
And then compare it to the second one, which is in Celsius. But the thing is, it breaks the Fahrenheit to Celsius, it's actually 86. Yeah. So, you know, you have to exactly the same number.
Yeah, you have to do that actually. I mean, so instead of doing that, you can just, as I said, you can put an error box. I mean, you just give a range. You say that I find it, they are equals if they are less than 0 or something, less than this value. The difference between the
Okay, so basically this here, I just changed the larger number.
Yeah, exactly.
You have some activity for that.
Yeah, we have SMT?
Yes,
Yeah, okay. Are you also doing that? Okay, okay, good.
okay.
It's in Miguel, no? For the this guy from Colorado.
Yeah.
Like the class.
Okay, yeah, I mean, I get understand later. Things are somewhat similar.
So it was understood.
Yeah, I could understand this on my background, but I think it's advanced for some people that haven't seen anything before yet.
Or hopefully.
Yeah, hopefully. I think the labs would be nice. I think the labs would be nice. So like you play with the thing and then see.
Only see the value and the location of home.
Okay.
The time between.
Yeah.
So the example is T.
Okay.
This is just
This convolution of frequency.
Is what?
Convolution.
Convolution. So what is convolution?
It basically, in the practical sense of what's going to happen, you're going to have the Fourier transform of your original system. So, you
No, I think it was advanced for people, but I was saying I think the lab would be nice because it would be like a theory and actually apply step by step, and we see like things working. I think like the complementation of the theory with labs would be perfect. Yeah.
you're going to take a copy of the original signal, scale it down, and then so, if you take the samples then you can have one replica of your original function overlapping with another.
Okay.
So that's called a data virus and so that I also become, you get one part of the symbol, circumpose.
Yeah, I understood.
So that's basically what I do.
Oh, okay.
And then that's if your symbol interference.